Hello, I'm Daniel Jordan. This screencast has been designed as a review of the experimental and computational thermodynamic models for drug inclusion complexes. So, why are we doing this? Well, pharmaceutical compounds can have a limited solubility in water. This leads to the restriction of the variety of potential formulations that can be developed. The reason behind this review is that drug inclusion complexes have become a key tool in the quest to improve the drug delivery or bioavailability. This is due to the simplicity and relative inexpensiveness of the reaction. Several other methods have been developed to try and combat the issue of drug delivery and bioavailability of poorly soluble drugs. However, this review will focus solely on inclusion complexes of pharmaceutical compounds. For a molecule to be able to act as an inclusion center, it must contain a hydrophobic cavity big enough to incorporate the drug that you wish to dissolve. The drug then orientates itself in such a way to fit its own hydrophobic region into this hydrophobic cavity, where there is no water molecules. The inclusion complex contains a hydrophilic exterior, which allows it to be dissolved. As the inclusion molecule is dissolved, the drug molecule is dissolved with it. Figure 1 shows how water molecules can leave the cavity in the inclusion molecule, in this case cyclodextrin, and the drug then maneuvers its way inside of the cavity. For the set of studies that will be reviewed, the focus is on inclusion complexes that occur in 1-to-1 ratios. This review is aimed to compare the use of two different types of method to examine thermodynamic processes in the formation of drug inclusion complexes, which will be computational and experimental. In terms of the experimental procedures that will be analysed, the main experimental technique we will be looking at is isothermal titration calorimetry, or ITC for short. This is a commonly used technique in the determination of thermodynamics, as it is one that gives enthalpy as an output value from the data collected. From here, the Van 't Hoff isotherm is used in the calculations to determine the remaining thermodynamic parameters such as Gibbs free energy and entropy by using the following equations. The Gibbs free energy is calculated by using the equation delta G equals minus RT ln Kb. The entropy is calculated by using the equation delta S equals R open brackets ln Kb plus delta H over RT close brackets. For each instance, R is the universal gas constant, T is a temperature, Kb is the binding constant between the drug and the inclusion molecule, and delta H is the enthalpy at the temperature T. Water models are originally based on the TIP model, which was a computational method that based any interactions with water on the assumption that water acted as a fixed or one-point system. This was adapted to become the TIP3P model, which considered each atom individually instead of collectively, named so as it is a 3-point system instead of a 1. This was then adapted to become a 4-point model, or TIP4P, where a dummy atom is theoretically added to each water molecule that bisects the two hydrogen atoms, which optimizes the structure of the water molecules involved in the calculation. Though it won't be covered properly in this review, a 5-point model also exists. This is where, instead of the presence of a dummy atom, the interactions of two lone pairs of electrons on the oxygen atom in a molecule of water are considered to make the 5 points, that is, the 3 atoms in each molecule of water and the 2 lone pairs. Rather unimaginatively, this model is named TIP5P. Cluster analysis is a computational tool often used to predict the docking of molecules. This technique is applied to systems that are heterogeneous and finds the homogeneous substrates that are then added together and combined with the results of a structure optimization to predict the final orientations and how the structure is docked in the compound. Mining minima calculations are a method to calculate binding free energy or Gibbs free energy that rely on estimates of configurational integrals instead of the usual sampling of conformations This means the method is less time exhaustive as it does not require as much time optimizing the compounds before the calculations can begin. This method also assumes the solvation process has completed for each of the calculations to occur. So let's look at some previous examples of thermodynamic studies using some of the discussed methods. First of all, let's look at a study by Andrew Fenley called Bridging Calorimetry and Simulation through Precise Calculations of Cucurbituryl Guest Binding Enthalpies. This was a computational study into seeing how 8 guest molecules thermodynamically interact with cucurbit 7-urel, and the paper saw the comparison of computational calculated enthalpies against the experimentally calculated ones using ITC. The 8 guest molecules were made up of 2 adamantanes, A1 and A2, 3 bicyclo 2,2,2 octanes, B2, B5 and B11, and 2 benzo bi-imidazoles, G8 and G9, and methyl viologen. There were 2 main aims to this paper. The first was to compare how the enthalpy differed between the computational and experimental methods taken, and the second was to demonstrate the potential that computational calorimetry has in determination and understanding of thermodynamics. The computational route for the thermodynamics involves 2 TIP models, the TIP3P and the TIP4P as discussed in the introduction, and the experimental route was the isothermal titration calorimetry. I would like to point out at this point that the paper makes no reference to the temperatures or temperature the experiments were run at. Rather, it was not until I went searching for TIP models I saw that one of the assumptions made from this model is that it must be done at 298 Kelvin. The results showed that the calculated enthalpic values for both models were considerably more negative than the experimental values. The enthalpy values differ between the models, which highlights the importance of the developments of considering all possible interactions. The changes in enthalpy values between the experimental and computational calculations did not differ by the same amount each time. This is because there are different optimization processes and hence different assumptions that must be made before the calculations can begin. The standard deviation values for the experimental and the computational method were between 0.1 and 0.3 kilocalories per mole, which shows the data is precise and reproducible in each instance. The next study we will look at is titled Molecular Dynamic Simulations of UC781 cyclodextrin inclusion complexes in aqueous solution. This is a computational study that used molecular dynamic simulations aimed to establish the orientation of the anti-HIV drug UC781 and 3 different cyclodextrin compounds. The 3 different cyclodextrin compounds are beta-cyclodextrin, 2,6-dimethyl beta-cyclodextrin, and 2-hydroxypropyl beta-cyclodextrin. This study used a range of computational methods to do this. It was understood that there were 2 possible orientations of the inclusion complex, shown in Figure 2. The aim of the study was to establish which of these orientations was most likely, i.e. the most thermodynamically stable, and also to prove it is the phenyl ring inside the cavity as opposed to the furane. The computational methods that we used are as follows, where the Cambridge crystallographic databases were used to find the initial geometries of all cyclodextrin compounds. The protein data bank was used to find the molecular geometries of the drug molecules. A Celeris DS Visualizer 2.0 was used to add the relevant hydrogen atoms to the molecules. Gaussian O3 was used to optimize the structures using the B3LYP calculation with a basis set of 6-31G with DP in brackets. AMBER 10 was then used for their own molecular dynamic simulations, coupled with AMBER 2003 and the TIP3P model was used for all water molecules. Shake algorithm was then used to satisfy the bond geometry constraints during the molecular dynamics simulations, and the cluster analysis used to establish the final structure as discussed earlier. The optimization showed the second orientation was correct, as it is known that the cavity had a radius of 3 angstroms, and therefore the distances further than that would have shown the molecule was not included in the cavity, which was the case for all of the examples involving orientation 1. The tilt angles were pushed closer to the perfect 90 degrees when the drug was included in the cavity. The energies showed the drug inclusion complexes had affinity order of the drug with the M-beta cyclodextrin had the highest affinity. The drug with the beta cyclodextrin then had the second highest, and the drug with the HP beta cyclodextrin had the lowest affinity of the three. This is known because there was a greater energy change seen for the M-beta cyclodextrin. Next is a study by Laura Waters entitled The Influence of Lipophilicity on Drug Cyclodextrin Interactions, a calorimetrics study. This study was experimentally based on the data collected using ITC, and saw drug inclusion complexes formed between 3 chiral NSAIDs, flurbiprofen, ibuprofen and ketoprofen, and 2 cyclodextrin complexes, beta cyclodextrin and the HP beta cyclodextrin discussed in the previous study. For each of the inclusion complexes, analysis was done at 3 different temperatures. The aims of this study were to calculate how the thermodynamics are different dependent on the different functionally related drugs in the cyclodextrin complex, to calculate how the thermodynamics of the drug complex change with a change in cyclodextrin, and to calculate how the thermodynamics of the complex are affected by a temperature change. The ITC experiments were carried out at 3 temperatures, 298 Kelvin, 303 Kelvin, and 310 Kelvin, the last of which is body temperature, which is important for pharmaceutical purposes as the drugs go into the body, and it's important to know how they will react once they're in there. The instrument was allowed to equilibrate at each temperature with the samples loaded before the collection of data began. The reference cell contained degassed pH 8 phosphate buffer where there was no significant mass loss after degassing. The samples were then stirred throughout the experiment at 300 revolutions per minute whilst the data collection was carried out. This was to ensure that nothing dropped out of solution. From the enthalpy values obtained from the data, the Van 't Hoff isotherm equations were applied, calculating the remaining thermodynamic parameters as discussed previously, and the binding constant at each temperature were calculated using Kb equals the concentration of the overall inclusion complex over the concentration of the drug times by the concentration of cyclodextrin. The order of spontaneity of the drug inclusion systems in terms of changing the drug was the flurbiprofen had the highest spontaneity, the ibuprofen had second highest, and the ketoprofen had the lowest. This was shown as the Gibbs free energy values were most negative for the flurbiprofen for each of the cyclodextrins. The order of spontaneity of the drug inclusion system in terms of changing the cyclodextrin was the beta cyclodextrin had a higher spontaneity than the HP beta cyclodextrin. Again, this is shown through the Gibbs free energy values being more negative for the beta cyclodextrin for each of the drugs. And at higher temperatures there was a higher spontaneity and more negative enthalpic values observed. The last of the studies is by Wei Chen, titled The Calculation of Cyclodextrin Binding Affinities, Energy, Entropy and Implications for Drug Design. This study used mining minima methods to calculate the Gibbs free energy of 5 guests inside 3 cyclodextrin hosts. The 5 guests were benzene, resorcinol, flurbiprofen, nabumetone, and naproxen. The 3 cyclodextrin hosts were alpha, beta, and gamma cyclodextrin. All reactions were simulated at room temperature. The aims of this study were to compare what effect changing the drug has on the Gibbs free energy and to compare what effect changing the cyclodextrin has on Gibbs free energy. This paper forms one complex that is the same as the previous paper. This means cross-comparison of the enthalpies can be made. This was the flurbiprofen beta-cyclodextrin at 298 degrees Kelvin complex. The problem was the Chen paper reported their findings as kilocalories per mole and the Waters paper reported theirs as kilojoules per mole. So I applied a conversion factor of 4.184. This was done by multiplying the Chen Gibbs values by the conversion factor, and this showed the experimental value was 3 kilojoules per mole more negative than the computational methods. So now we're going to talk about the positive aspects of each thermodynamic method. Computational methods can be used to predict the docking and energies of large molecules, which can be used to establish if it's worth proceeding experimentally in terms of the drug inclusion complexes. For drug inclusion complexes, if the drug does not computationally dock as you would like it to, so that would be if the hydrophobic region wasn't in the cavity, or the required energies for the reaction are too high, it is not worth carrying out experimentally. Another benefit to computational methods is that all mathematical calculations are done by the computer. This means there is less chance of the calculations going awry because of misinterpretation or false rearrangement of the calculations. The chances of human error are reduced by computational methods in general. One type of human error was just covered, however, you can also see human error occur in the actual experimental procedure. For instance, if this was to occur, then inaccurate or skewed results would ensue. Computational methods are also environmentally cleaner, as there is no need for the raw materials or to carry out any reactions at all that could have a negative impact on the environment due to the reaction or improper waste disposal. In terms of the experimental methods, more accurate values are obtained as the values are not based on as many assumptions. They are less time exhaustive than computational methods that can take hours or days to complete, and it is cheaper to do the experiments with less training required, as anyone can load a sample into the instrument, you would hope. Contrastly, computational methods are time exhaustive, expensive, and require training on how to use the software. Computational methods also provide less accurate results as they are heavily dependent on assumptions. However, this is improving in the sense that assumptions that are made more recently have become more relevant and more true to life. This is seen through the development of the 3, 4, and 5-point TIP models. Experimental methods can come with complicated mathematical interpretation, which increases the chances of human error in the calculation. There is also a chance of human error being carried out in the practical experiment, as someone could add incorrect amounts of the compound, which would cause, or inconsistent amounts of the compound, which would cause less precise results and less reproducible results. Experimental methods also use raw materials, which, as discussed, could have a negative environmental impact. So I'm now going to talk about the future work that I think should occur. I think future work should include altering the chemical ratios used in experiments, as all studies we looked at were 1-to-1 ratios. I think it could be beneficial for research to expand into looking at the impact of forming ratios of 2-to-1 in favour of the inclusion molecule. In doing this, both ends of the drug can be included for further improving the solubility. In improving the solubility, there should be a reduction in the amount of energy exchange in the process of solvation. This should be investigated in a similar way to the studies discussed. This could allow for the advancement of drugs containing two hydrophobic areas, such as phototoxin structure, where the structure is shown in figure 3, or drugs where the not hydrophobic part of the drug isn't hydrophilic, such as straight alkyl chains with a reactive drug group at one end. Thank you.